Hello, I'm Mike McCulloch. So today I'd like to talk to you about the Tajmar effect, or the Tajmar experiment, which were a series of tests done by Martin Tajmar and his team in Dresden, in Germany, or I think originally they were in Austria as well. So these were done between about 2003 and 2009, and what they did was they took a stainless steel ring, put it in a cryostat, cooled it down, and then they span it, and they found that when they span it, gyroscopes in the vicinity span with the ring only very slightly. So the spin of the gyroscopes was only about 3 times 10 to the minus 8 times the spin of the ring itself, but it was significant, and they recorded that. They found also that there was a parity violation in that when they span the ring anticlockwise, so that is in the same sense as the rotation of the Earth, then that meant that the actual the spin was reduced. The spin of the gyroscope was reduced, and when it was clockwise, it was enhanced. It was double, approximately double. So this was a very interesting result, and I became interested in this result very soon after I looked at the flyby anomalies, which, if you know about them, these are I've discussed these before, but this is when a spacecraft comes into the Earth at the equator, and the accelerations between the spacecraft and the equator are large, and then it leaves along the polar axis, and the accelerations are lower, and so the spacecraft loses inertial mass, because that's what happens in QI, and gains speed. And this seemed to predict the flyby anomalies very well. Well, this is kind of similar because it involves a spin. So I started looking at this, and I found out I could predict it very simply. So what I think is happening is that, so when they put the ring into a cryostat, all local accelerations were reduced by the cooling. So so that would mean that the underwaves waves seen by the disk and the gyroscope were longer, much longer, and more of them would be disallowed by the cosmic horizon, and so their inertial mass would reduce. And then as soon as the disks were spun, that adds an extra very quantifiable acceleration into the system. So we know exactly what it is. You can calculate spin very easily, and this acceleration causes the underwaves waves to shrink, so more of them fit within the cosmic diameter, and so the inertial mass goes up. And in order to conserve momentum, the gyroscope has to spin with the ring. And so I worked out the mathematics for this, and I also considered the acceleration of the gyroscope with respect to everything. That's very important. So not just with respect to the disk is accelerating with respect to the gyroscope, but also the gyroscope's acceleration with respect to the fixed stars, so the cosmos itself. And this is crucial in getting a parity violation. So if you do that, you can work out that the spin of the disk at, it was Siebersdorf, Austria, at first, relative to the fixed stars, is the acceleration, spin acceleration is something like 0.03 meters per second, and the spin of the disk itself was about 2.5 meters per second, the acceleration of that spin. What I also did, and I assumed this based on gravity, is that the importance of everything in the vicinity for the inertial mass of the thing that's accelerating is proportional to 1 over r squared. So I added that in there, that assumption in there. And when you do that, you see that the as soon as the disk starts to spin, well, first of all, the gyroscope only has an acceleration relative to the fixed stars, so that gives it a certain inertial mass for the system. And then when you spin the disk, it also has an acceleration relative to the very close disk, so that also gives it a relative acceleration that you have to consider. So that increases the inertial mass. For the momentum of the system, to be conserved, the gyroscope has to spin with the ring. So I calculated how much that spin was, and it agreed exactly with the spin observed, which was about 3 times 10 to the minus 8 times the disk's spin. And it also made a difference, because if you spin the disk in the same direction as the Earth, then the gyroscope will also spin very slightly in the direction of the Earth, and that will increase its acceleration with respect to the fixed stars. But if you do it the other way, it has the opposite effect. So that gives you the parity violation very, very nicely. So I published that result in this paper in 2011, and this was the first paper I actually won a best of award from the journal. I think I wrote a couple of papers about it, and I think I got an award for both of them. A best of award from the journal. So yeah, so this was a very nice result, and it also predicts that if you do the experiment in the southern hemisphere, for example, the parity violation should be reversed, which makes sense. And I believe there has been a test done in New Zealand, although I can't find much information on it. And when I spoke to Martin Tajmar once, he said that the parity violation was indeed reversed, but I don't have a backup for that yet. In the paper, I also predicted that one way you could test this is to take a ring which is much lighter and spin that, and then this 1/r rule should start to show up in the results. So nearby gyroscopes should have a much larger spin than gyroscopes further away. So that would be a potential test. And it's also very nice in terms of Mach's principle. Mach always said that the inertial mass here is relative to masses out there, and this kind of quantifies that thought, that philosophy. Okay, so I hope you've enjoyed this short, and I look forward to seeing you next time. Goodbye.